So here the question reads, with the aid of a diagram, explain the working of the following logic gates. So the first gate that I've put there is a NOT gate. Okay, so it says with the aid of a diagram, explain the working of the gate. So I'll draw the diagram there. The NOT gate looks like that. So you have an input, and then the input A will be complemented like that. Okay, that is how this gate operates. So now, how do you answer this question? So you draw a diagram of the gate, you explain how its operation, and then maybe draw a simple truth table. That's all you do on this question. So like a NOT gate, in the case of a NOT gate, we're going to say a NOT gate is just used to perform a complement of input bits. So NOT gate is used to perform a complement operation of input bits. Okay, that's what you write. So a NOT gate is used to perform complement operation of what, of input bits. Then what does that mean? That actually means, okay, if one is input, 0 is output, 0 is output, and vice versa. Okay, that's what it is. So then the truth table will be as follows. So you have an input here, you have an output. If you input 0, you get a 1. If you input a 1, you get a 0. So that's all you're going to write on the NOT gate. So the second answer is an AND gate. So an AND gate is going to take this shape. So an AND gate is going to take this shape. It looks like this. Okay, so say input A, input B, in output, but we have an AND gate here. Then it does multiplication, right, of the input bits. So now what we're going to write about an AND gate. So an AND gate is just simply a logic gate that requires the all inputs to be true to give a true output. So it's just a gate. So this one requires all inputs to be true to give a true output. Okay, that's what an AND gate does for us. An AND gate is just simply a logic gate that requires both inputs to be true to give a true output. And the truth table is as simple as you have input A, you have input B, then an output Y. So if you have 0, you have 0, 0, you have 1, 1, 0, 1, 0, 1. Okay, so in that regard, if 0, 0 give you 0, 0, 1 is going to give you 0, 1, 0 give you 0, 1, 1 is going to give you 1. So here both inputs are active, so it will give you a high. So that's what you write about an AND gate. Then on the third part, we are required to talk about an OR gate. Okay, so an OR gate. What are you going to say about an OR gate? So an OR gate, the shape looks like this. The OR inputs A and what? And B. So an OR gate is just simply it's a logic gate or a logic circuit that requires one input to be true to give a true output. Okay, so it just requires one true input to give a true output. Okay, so it requires one, this one just simply requires one true input to give a true output. So the truth table will look A, B, and Y. Okay, and from there we'll have 0, 0, 1, 1, we'll have 0, 1, 0, 1. So that is going to be one input to be true, right? So here one input is true, we have a 1. One input is true, we have a 1. If both inputs are true, we have a 1, 0, 0, we have a 0. So that is how an OR gate operates. That's what you write about an OR gate. And from an OR gate, you have to write about an exclusive OR gate. So exclusive OR gate. So what is it about an exclusive OR gate that we are going to write? So about an exclusive OR gate, we know that it's a strict form of an OR gate. So this one strictly requires only one input to be true to give a true output. Okay. So design looks like this. An illustration XOR. Okay, so we have A, we have B. So it's a logic that requires only one true input to give a true output. Okay, so it requires only one true input to give a true output. So if you look at an OR gate can have 1, 1 like this and to give you a true output. But for an OR gate, it's the opposite case. Okay, so we're going to say A plus B for an OR gate. Then for an exclusive OR gate, here in the design, it's going to be A, then plus in a circle, then you say B. That's how it looks like. Then the truth table is going to be A, B, then Y. So 0, 0, 1, 1. So 0, 1, 0, 1. So what will happen is that when you say 0, 0, it's going to give us a 0. 0, 1 to be a 1. 1, 0 to be a 1. 1, 1 will be a 0. Okay, so an exclusive OR gate strictly requires only one true output to give you, one true input to give you a true output. Okay, so now we're going to look at an exclusive NOR gate. Okay, so with an exclusive NOR gate, it requires both inputs to either be true or false to give a true output. Okay, so the design will look like this. Exclusive NOR. So you have A, you have B. So you have an exclusive NOR gate. Okay, what happens? It requires both inputs. To either be true or false. Either be true or false to give a true output. Give a true output. So what will happen is this. So our truth table is going to look like this. We're going to say A, B, and output Y. 0, 0, 1, 1, then 0, 1, 0, 1. So both of these are false, so we're going to have a 1. This is a 0, this is a 0. Both of these are true, so we're going to have a 1. That is how an exclusive NOR gate is going to operate. So we have we've looked at a NOT, an AND gate, looked at an OR gate, an exclusive OR gate, and looked at an exclusive NOR. So the last type of a gate that we're supposed to look at in this question is the NAND gate. So with the NAND gate, so we know that so a NAND gate requires both inputs to be false to give a true output. Okay. So the way it looks an AND gate. It is got this 0, this small circle in front like this. So it's a combination of an AND and a NOT gate. So we have A, B, but with a bar like this. So it requires both inputs. To be forced to give a true output. Requires both inputs to be forced to give a true output. That is what will happen with this gate. So the way it's going to look like, you're going to have the truth table will be A, B, and Y. So 0, 0, 1, 1, 0, 1, 0, 1. Okay, so both of these are false here on top. This is false, so we're going to have the 1. Then the remainder will be 0, 0. Okay, so that is how you answer, this is how you're going to answer the 2024 question paper, question 7A. Okay, so you have not and or exclusive no, and then the AND gate.